Hey mechanics friends, in this video I want to talk a little bit about the difference between elastic and plastic strains, and also talk a little bit about unloading and reloading behavior of materials. Particularly we'll talk in terms of ductile metals. Alright, so hopefully from last lesson you remember the difference between elastic strain and plastic strain. So elastic strains, the strains are recoverable. Basically, the material returns to its original shape when unloaded, whereas plastic strains, permanent deformation can occur. If you want to have a little bit of a visual there, think elastic, right? Elastic, I think of like a bungee cord, a rubber band or something like that. When I pull on it, when I release that force, I come back to the original shape, right? So I pull on it, back to the original shape. So these are all elastic strains, right? The same thing happens in metals, just at a very low amount, right? We sometimes can't always see the elastic strain that happens in metal because of its high modulus of elasticity or high stiffness. Now when we talk about plastic strains, we're talking about things that stretch. And so when we talk about plastic, right, I think of plastic like a plastic bag. If I was to pull on the plastic bag, and I would pull on it, much like I did a structural member, it would deform. Now, at this point, I have plastic deformation because I have permanent deformation. Hopefully you saw that stretch in there. Now, when I release the force, I have some recovery, so that's my elastic recovery, but I still am left with a much larger object than I started with, and I have a lot of plastic deformation. So hopefully that helps visualize, helps you visualize the difference between plastic and elastic deformations. So next I want to talk a little bit about unloading and reloading behavior. Alright, so let's talk a little bit about the unloading and reloading behavior of a ductile metal such as steel. So if we go through, we want to plot the stress-strain curve, so hopefully we're getting good at this. Stress on the y-axis, strain on the x-axis. We go through, and when we would start, initially we have what we call the linear elastic range. Now, what happens if I stop right here and I hold it steady? So I know I went up on some modulus of elasticity E, I stopped it, and now I hold it steady. So I'll say this is 1. Alright, if I hold it steady, it's just going to remain here. There'll be some stretch, and then it'll be at some stress. Now, what happens if I release it? As you might suspect, in the linear elastic range, because everything's elastic, if I release my force, I will come back to 0. So I'll come right back down this curve, and I'll end at this point back at 0, 0. So all my strains at this point, the strain that I had was recoverable. Remember, I could come down here and figure out what the strain was at point 1, and then all of that strain was recovered. So that's what we call elastic strain. Alright, now let's say I reload it. So I start to load it up again. It's going to follow the same path back up. And it'll keep going up. Eventually I'll hit yielding, and it'll go out to some point here. Now, once I have yielding, right, yielding is now, one of our definitions for yielding was that plastic deformation has now occurred. Now I'll have some permanent strain or permanent deformation in my member. Now how do I figure out what kind of permanent deformation I have? So what happens, what do you think would happen if I release this? Well, hopefully you remember back to the plastic bag demonstration, right? When I released it, I still had some recovery. So if I was to release this point, the stress at this point, I would start to have some elastic recovery. But of course I won't recover all of it, namely I won't recover this amount of strain that happened. So as it turns out, we'll track basically back down a path that is parallel to our modulus of elasticity back until we get to 0 force. But now you'll see that at 0 force, I have some plastic strain remaining in my member. And then at this point, if I was to jot down, this would be my elastic strain that I was able to recover. This would be the same elastic strain that I would have at this first point. All right, so hopefully you kind of getting the idea of this. If I was to reload, so let's see, this is stage 4. If I was to reload my 5th step, I would start coming back up. I would actually track right back along the same line. Now when I get here, something funny will happen. I'll have to kind of overcome that initial inertia to get yielding to start again. So I might see a little bit of a rise in stress. But nothing major. It'll keep going out. I could head up into strain hardening. And now I'm going to stop it up here in strain hardening. If I do that, I can then stop it. I could release it. And if we release it here, just like when we did from the yield plateau, we'll track parallel to the modulus of elasticity. So it'll come down a path that's parallel. Again, if I was interested in coming up with the strains at these points, this would be my elastic strain or my recoverable strain, and then this would be my plastic strain. Now to figure out what some of these points are, I'll just kind of make the general note. We can always use linear algebra to solve our epsilon sigma coordinates on the stress strain curve. So this is all just a big linear algebra problem, right? If we knew where we stopped it at 0.5 and we knew the slope of this line, we could find coordinates for this point down here at 0.6. And then we could figure out the coordinates here would then be our plastic strain. We could take this value, subtract our plastic strain to get our elastic strain. So hopefully, we might do a little bit with these calculations in our class, but hopefully that makes some sense. Another thing that's valuable is a lot of times we want to know the deformation at a certain point. So if we take whatever the strain is, remember, if we take our strain is delta L over L0. So if we're interested in delta L, at any point along the curve, we can take our strain, multiply it by L0 to get the amount of deformation that's occurring in our member. All right, finally, in our final step here, if I was to increase the load again, it would come right back up, kind of join back in, hit the ultimate load, come down to necking, ultimately fracture, and this will be our final stage. All right, so hopefully that gives you a little bit of insight into the unloading and reloading behavior of metals. If you have any questions, be sure to let me know. Otherwise, I'll take a look at a word from our sponsor. Now, they're not really our sponsors, but I want you to think about Jello, and we're going to jump into the next video when we talk about Poisson's ratio and see how Jello is going to help our understanding of that engineering property.